I'm Dave Austin, the Executive Director of the Institute for Energy Efficiency. In prior years at this conference, we had a number of requests to give you a little taste of some of the research that's going on at UCSB in the Institute for Energy Efficiency. And so for that reason, we've put together a session of 3 speakers who you will now hear. They'll give you a flavor of some of the things that we're doing in this area. And to host and moderate that session, we have Mike Witherell, who is our Vice Chancellor for Research at UCSB. Mike is a very high energy guy and also was very involved in the field of energy as director of Fermi National Lab for 7 years. Mike?
So I was the part of the Department of Energy who was the biggest consumer of energy around Chicago, actually, at Fermi Lab during that time. So it's my great pleasure to serve as moderator for the next session, which will feature some of the research highlights from the Institute for Energy Efficiency, as you heard. One of the best parts of my job as Vice Chancellor for Research is to tell people about our place in the world of research universities. In the areas of physical sciences and engineering, you heard some from our Chancellor this morning. We ranked easily among the top 10 research universities in the recent rankings by the National Research Council. But in fact, it's broader than a national ranking. When the academic ranking of world universities based in Shanghai did their ranking, we were in the top 20 in both engineering and technology and in natural sciences. And for the European version, the Times Higher Education ranking from London agrees. They put us in the top 20 in the world in both engineering and in physical sciences. So it's a pretty clear picture. A few years ago, the leaders of engineering and the sciences at UCSB spent some time thinking about how we, as a leading research university, could make the most significant impact on the energy issues facing the country. So across the country, as you know, institutions are working on technologies that could help provide long-term energy security, minimize carbon emissions, support the economy as well. Every developed country in the world, in fact, is facing some version of these issues, and we wanted to maximize what our impact was in that environment. So for us at UC Santa Barbara, the answer was to establish the Institute for Energy Efficiency. In coming to this conclusion, we started with the fact that we are the nation's leading research university in materials science and engineering, #1 ranked in the NRC rankings. In addition, we have outstanding research programs in energy-related sciences, engineering, environmental economics, and policy. And when we assessed our position and the national and global needs, it became clear that we could make the greatest mark by applying our existing strengths to energy efficiency, broadly defined. So that's what led us to the Institute for Energy Efficiency. And what we actually do here is, as all research universities do, research, communication, and education. So the Institute integrates faculty research across and beyond the campus, and you will hear a lot of that at our session today. Communication, communicating key issues related to the science, engineering, and policy of energy efficiency, and in fact, this meeting is part of that. And education, we are working very hard to educate a new generation of technology experts and policy experts on the emerging energy economy. So, we have very clear ideas about what we should be doing, and the research leaders of the Institute have developed the following solutions as their primary goals. A $1 LED light bulb, 20 times more efficient than an incandescent bulb. Solar cells with double efficiency at 1/10 the cost. Economically viable zero net energy building systems. Wireless and optical technologies for super high performance communications. A new Moore's law for more energy efficient computing. And worldwide energy efficiency, policy direction, measurements, and standards. We have areas working in people working in all of these areas, and today we can't take up the whole afternoon with these, but we have some of the stars of this group are coming to talk about their research highlights today. So at our session, to give you a preview, we have first John Bowers, who's the director of the Institute, you've already heard from today, and he will talk about breakthroughs in silicon photonics. Then we'll hear from Dan Morse, founding director of the Institute for Collaborative Biotechnologies, talking about biologically inspired high-powered batteries. And finally, Jim Speck, who's the director of the Center for Wide Bandgap Semiconductors, will talk about the dawn of solid-state lighting. So they're all pretty interesting areas and areas in which UCSB and the Institute for Energy Efficiency have a lead. So I'll start by introducing John Bowers. He's the Fred Kavli Chair in Nanotechnology. He's the director of the Institute for Energy Efficiency and of the Center for Energy Efficient Materials, which is the Energy Frontier Research Center that Bill Brinkman talked about. He's a member of the National Academy for Engineering. He, with his colleagues at Intel, built the first electrically powered hybrid silicon laser that got a big stir a couple of years ago. And he is going to talk today about the energy efficient photonics revolution. So.
Well, thank you, Michael. I'm very glad to be here to talk about this. I'd like to acknowledge a number of people, particularly Larry Calderon and Dan Blumenthal, who I collaborate closely with. And then a number of students who do most of the work, and a number of companies, Intel in particular, as well as Orion, located in Santa Barbara, and Hewlett-Packard. So, as Mike said, there's 6 areas of the Institute, and the talks this afternoon will primarily focus on 2, electronics, photonics, and computing, in terms of the work that I'll describe, and then a supercomputing section that comes next. The problem we're addressing is that the Internet is growing very quickly, right, doubling every 18 months, and this requires increasing amounts of power. So the solution we're going to talk about is using photonics to communicate that data across data centers, across supercomputers, across the world, and talk in particular about doing this on silicon as a low-cost way to do this. And look at the impact on supercomputers and data centers, and we'll hear much more about that later in the afternoon. So that's kind of an overview of what I want to talk about. This slide from Intel talks about all the data that's being generated. We've all seen this from Google Earth and the ability to look at your house and everything else. There's increasing amounts of data becoming available. You know, a zettabyte's a lot of data. It's 2 to the 70th power, right? That's where we're at now. And so I think Bill talked about exascale computing, exabytes. A zeta is 1,000 of those, 10 to the 21. And that's a lot of data being generated, and it's all typically stored somewhere in a cloud, and that needs to be communicated to all of us to become useful. And so as a consequence, the traffic is growing very rapidly. A number that people often use is 2 dB per year, which means in 5 years, that's 10 dB. That's 10 times the traffic you had before. So every 5 years, you have to have 10 times that communication capability. And the problem is if it takes the same amount of power, then you're really in a problem, right? Because in 5 years, the internet will take 10 times the power it does today. So maybe it's 4% today. That's 40% in 5 years. And at the end, a decade from now, that's 440, more than a factor of 2 higher. So that's the point. 10 years is 20 dB is 100 times. And if you look at what the causes of that are, this is a Cisco study. It's changing. There's a lot of different aspects to it. You probably can't see it, but it's video on demand and things like this. And increasingly now, where we're moving to is basically internet video to your home or to your PC. And so there isn't any indication that this is slowing down, but will continue for quite a long time. Photonics, in response to that, has been growing its capability. So the first photonic transmission systems were back about 1980, kind of somewhere below the floor here at about 50 megabit per second. And more recently, there have been a whole series of inventions that have gone on. And so we're now basically up to sort of 10 terabits or maybe 20 or 30 terabits. And the belief is that will continue to expand. So we will be able to provide that information. The question is, can we do it cost effectively and power efficiently? If it takes 10 times as much power, we're all, or 10 times as much money, we're definitely in trouble. So today, most of us on our computers have 10 gigabit connections. Routers these days are just moving to 100 gigabit connections in the front face of all of those. And the belief is that in 5, 10 years will move to a terabit. And so one issue is how do you get to this terabit optical Ethernet? And there's a bunch of ways that will happen. Part of it's by signaling at ever higher speeds. As silicon gets faster, then clock speeds will get faster. So today, 5, 10 gigahertz is common. It'll move to 25 fairly soon, and probably beyond that in the future. Part of it is by having ever more colors of light traveling down the fiber. So this is called coarse WDM. So this is what's common in very inexpensive systems where they don't have any temperature control, but 6 or 8 wavelengths of light. Way out here, one gets to typical systems for long haul are perhaps 100 or maybe 200 colors of light. Again, that way you can take, say, 10 gigabit with 100 colors, get you to a terabit per second. The other big area of research is more complex modulation formats. So just like your cell phone has, some high level of modulation format to get lots of bits per hertz. So the transmission spectrum over cell phone towers is very limited. So already they have gone to more complex modulation scheme. For the most part, optics today is back here. 99.9% of all optics is just on-off. Just turn the light on and off, basically, and that's it. But increasingly, these very complex modulation schemes, like we have in cell phones, are what will happen in photonics. So the capability is there to do it. But typically, these complex modulation schemes are very expensive, and they take a lot of power. So those are the issues we have to work on. The other thing which is happening these days, and this is a very hot topic in the research conferences, is this line of space division multiplexing. So today, down an optical fiber, you have one beam traveling down it, perhaps many colors of light. But the focus now is to get typically 7 beams of light down a fiber. So there would be 6 around the outside, 1 down the center. And again, that just means at the end of that fiber, you've got a very complex receiver that now has 7 times as many things on it as you used to have. So the general point of all this is photonics is getting very complex, lots of parts. And so there have been efforts to integrate. This is, frankly, where today most of the industry is still at. Every time you have a different color of light on that fiber, there's a separate laser for it. There's a wavelength blocker for it. There's a modulator. There's perhaps backface detectors. And then all these get combined in a single wavelength combiner. And where that's moving towards, integrating all those components on a chip. That's absolutely essential, because this is really expensive, right? All these have devices in a package with a fiber coupled to it. And you add all that up, and you've got 40 or 50 fiber connections, and each of them with a separate power supply and electronic connection, things like that. This is really where the world's going. But this is really not very much, right? This is 100 gigabit per second. That's very primitive compared to most of what I just talked about in the previous slide. So there is a lot of research at UCSB going on in this area. There's a center that Larry Calderon runs called PICO for photonic integration for coherent optics. So its goal is to make things like these complicated receivers that do coherent demodulation of signals or transmission of signals. And there's other sorts of photonic crystals and a whole roadmap of where that center is going. There's another center, the Terabit Optical Ethernet Center, that Dan Blumenthal runs and was announced about 9 months ago. And again, you've seen this chart already in terms of how do we expand capability. And that's with many colors of light, many wavelengths, hundreds of wavelengths. The single wavelength approach is down here, and the roadmap that Dan is advocating is here. And within 10 years, the goal is on a single color to get a terabit of data. And then if you have 100 colors of light, you have 100 terabits going down that fiber. And so it's drawn down here as a cartoon, but of a fairly complex optical circuit that will accomplish all of that, coupled to a very complex field SI circuit that does all the control and reading of data. So that's another big effort at UCSB. As a result of this integration of parts, this is kind of where we stand today. So, pretty much back in the early 80s, back sort of a gigabit per second data transmission, there was typically one device in a package, one laser. And increasingly in research, we've gone up to levels like this, and this is work out of Dan Blumenthal and Larry Calderon's group, this motor chip that is shown there on the top. And that is state of the art, 300 elements linked together. So that's good, but that's, again, not where we need to be in 5 or 10 years. So our whole group effort now is how to make something much more complex than that. And a lot of our focus in the Institute is doing this on silicon. And there's a very rich, strong process technology in silicon that goes way beyond, orders of magnitude beyond where photonics industry is. So today, you know, there's 7 billion transistors on a chip. That's, you know, very high yield, very high levels of integration. We want to apply that to the photonics industry. And so here's one viewpoint. This happens to be an IBM slide of what they're looking at for supercomputing. And the idea is you've got a plane of processor chips. So you've got, you know, hundreds of processors, hundreds of cores on a chip. And that's bonded to a memory plane. So again, the advantage of that is that the delays between memory and the processor are now very short. And you might have multiple memory planes to get sufficient memory close to that. And then you have a photonics plane on that. So these are all just chips bonded on top of each other. And these different cores, these are supposed to, these black squares represent different cores in this processor, are then all connected optically. And the reason they're connected optically is that you've got 200 data lines at a 5 gigahertz rate. That's a terabit per second going from each of those cores. So on that chip, you're going to have something like 500 terabits of transmission. That's not unlike sort of a national sort of level today integrated onto a chip. And the goal is this will happen long before we get to exascale computing. So it's something that has to happen within the next 10 years. So we'd like to do this. The problem with this is that silicon is indirect band gap. It inherently doesn't emit light. If you forward bias a p-n junction, it gives out heat, phonons, rather than light. Second problem is because it's indirect gap, it's a really lousy absorber. People don't make detectors out of silicon today. Silicon is centrosymmetric, which means it's a lousy modulator. These are all the reasons that the photonic industry is based on indium phosphide and gallium arsenide. They don't have all of these problems. There's SiO2 layer and SOI wafers. That's resistive. That's a problem. And then finally, silicon is reciprocal, which means that it transmits inherently the same both directions. And most photonic devices need isolators. And so they need a non-reciprocal element. So that's the problem. That's what we're trying to address in this. If we are successful, then what we can do, though, is combine all the laser technology we've seen, do it in a silicon CMOS foundry with all the complexities and capabilities of CMOS, and end up with something that takes us many generations forward. So photonic integrated circuits today are on these sorts of sizes. They're probably too low to see, but fairly small wafers, 2 or 3 inch diameter wafers, fairly coarse levels of lithography. And if we can make all these photonic devices we just shown on silicon, we can directly move to a modern silicon CMOS foundry and jump literally 6 generations of technology. And that's our goal. That's what we're trying to do. The approach that we have pioneered in the Institute is to put layers of 3-5 materials. So these 3-5 materials are direct band gap, they're efficient light emitters, they're efficient detectors, they're efficient modulators, and put them directly on silicon substrates and then run them through a CMOS foundry. And the 2 partners we work with in this, or 3, actually all 3, but in particular Intel and Orion run these parts through conventional CMOS foundries today. You can make a lot of different devices. This happens to be one particular device, what's called a distributed feedback laser. The point being that when you look at the light emission out of it, it only emits at one very particular, very well-defined narrow wavelength. And that's critical because we want to combine hundreds of these together. And each one has to be very precisely positioned. And again, because the gratings that determine that wavelength, these little dots right here, are very precisely determined in a CMOS foundry, we can hit those levels of control. This is one of the chips that one of my students made, Siddharth Jain. But the point of it is that we're now at the point where we combine 16 different wavelengths together on one chip. Or in that case over there, 16 wavelengths with 16 modulators and detectors. So again, not huge amounts of integration, right? You know, on the order of 60 elements on a device. But we'll get in a second to where we want to go. And the point being that we can now get 16 colors of light. And the next issue is, can we modulate those fast enough to get to these sorts of terabit speeds? The other issue, this is a conference on energy efficiency, but in particular for supercomputing, Bill Brinkman mentioned the problem of, we can't have gigawatts of power in our exascale computer. The connectivity has to be very low power. And so today our threshold currents are up here at say 50 or 60 milliamps. And we're now looking at how do you get down to sub-milliamp. And we've gotten fairly close to that, about 2 milliamps. We're trying to get lower. But in particular, there's certain types of lasers. These are ring lasers. And this is a wafer with literally something like 1 million ring lasers on it. And the point being, the number that I want you to remember for a second now is if we operate this at 10 milliamps at 1 volt, that takes 10 milliwatts. And if we operate that at 25 gigabit, which is the next standard, after 10 gigabit in a data center will be 25 gigabit, that requires about 0.4 picojoule per bit. So remember that number. We have to get lower than ultimately, but to break in, we need to hit 0.4 picojoule per bit. So that's two elements of it, lots of wavelengths, low power. The other wavelength is, can we make fast modulators? So again, this is a silicon wafer, and the point being it runs at 50 gigabit per second. So where we're going to head with this is 50 gigabit times 20 wavelengths is a terabit. So we're not too far away from being able to get there with this technology. This is some work out of Intel. So they had a press release on this last summer. Justin Ratner is the CTO at Intel. And they discussed a 50 gigabit per second link, which is processed in a CMOS foundry. It uses a lot of these same ideas. So in this case, there's 4 colors of light, 4 hybrid silicon lasers. There's 4 modulators. They combine it together. It's all in one chip. And they can make this in a CMOS foundry and make it very low cost. Mario Panicia, who runs this effort, his whole thing is this has to cost $1, right? He has to put this on a laptop and make it cost effective. The question is, where do you go from there? And so that's where this is now, 12 gigabit per second, 4 wavelengths, 50 gigabit. We now want to get to, say, 25 gigabit, 16 wavelengths, or maybe 40 wavelengths, then we get to a terabit. And so that's kind of where it's going, and we've got the elements to get there. There are a lot of other devices one needs, and we work on all those other elements. These are all things we've demonstrated that one needs to make a real optical system. I want to talk about, just briefly, just to close up, a few things that tie into later sessions, talks in this session. But there's a big problem with making routers. And a modern Cisco CRS1 router, if you fully put it out, takes something like 1 megawatt of power for just that one router. There's an effort at UCSB on what's called the Laser Project to build an all-optical router. And it's in collaboration with Cisco. And Dan Blumenthal runs it. And here's some of the chips that are being made in it. But again, they all require lots of integration of lots of optical elements together. And the goal is to make something that takes a small fraction of that megawatt of power, or equivalently takes a megawatt of power to handle 100 or 1,000 times as much data. There's another project at UCSB called IFOD, and the goal is to now reduce the losses, optical losses on fibers. And those are working really quite well. The losses today are literally 50 times lower than silicon. It's on a silicon wafer, but it's a different wafer technology. And you can make very high Q resonators, literally Qs of 18 million on a chip, which is unprecedented. In terms of data centers, there is this push. Data centers are now looking at 100 gigabit interfaces, but 100 gigabit switching devices don't exist yet. Theoretically, optically, you can do much better. This is power, again, it's nanojoules per bit, but so this is a picojoule per bit. But optically, you can switch data with a lot less power than electrical. And that's inherent, because electrically, you look at every bit. You process every bit in a computer. Optically, it just flows through. You just sort of switching a stream around one way or the other. And inherently, it's lower power. In terms of high-performance computing, we'll hear a lot more about that today. This is one example of one of the IBM systems. And the point being that there are fibers on these today. So these are all optical fibers running in. So they're running in close to chips. But increasingly, they're going to move onto chips. And that's the real drive to put photonics on silicon, is to make all that just much denser. One of the big ways that's being done today is with vertical cavity lasers. That's probably the dominant technology in a data center today. And Larry Calderon's working extensively on this. And they got some of the best results in the world at 25 and 35 gigabits per VCSEL. And they have ideas for how do you move further, perhaps 50 or 100 gigabits per second. And so that's another important effort of what's going on at UCSB. This is an old slide. This is actually 10 years old, but I wanted to bring it up. It's Steve Wallach, who started a couple supercomputer companies, Convex being one of them, Convey being the other. And his idea is that, again, you use optical switches to combine racks of supercomputing elements together and use the fact that these switches are very low power. And so that's one person's vision of where the world's going. If you can get these very low power levels, and I mentioned 0.4 picojoule per bit is where we're basically at today, you can save a lot of power. So these are all the world's supercomputers, or at least the top 10 or 15 computers. Here's the 2 petaflop number. And so higher throughput is up here. Bill mentioned we want to get, obviously, to exascale, so you want to go 50 times above this, or 10 times, 100 times above that level. And what's going this way is power is this way. So this is bad over here. Goodness is over there. And so here's all these different computers that all fit on a straight line. The point of this curve is this. If we can reduce the power of optically interconnecting these supercomputers to on the order of a picojoule per bit, it's this line right here, then we can save a factor of 100 in the power of that supercomputer. So that's the goal. We need to make very high radix, very high port count, very high speed, but very low power. So we can hit a picojoule per bit. We can probably hit it 100 femtojoules per bit. And then you're actually talking about another factor of 10 below. So then you really can go from 2 petaflops to 2 exaflops and have the same power in terms of interconnecting those. So to summarize, I've talked about things that photonics can do, lower power, more efficient ways to communicate. Today, it's ubiquitous at a wide area, even a local area, right? We now increasingly have fibers going to our home. That's going to keep getting closer and closer within data centers, onto chips, and within supercomputers. These complex ways of getting more data onto a chip require lots of elements. And so integration becomes absolutely essential for size, weight, power, and making it very inexpensive. And personally, I think doing things in a CMOS foundry in a hybrid silicon way is the way to get that process technology. So thank you.
Okay, thank you, John. So these are different enough topics, we're going to take questions in between the talks. So any questions for John? So, Bill, do we have a...
This kind of technology, what are you doing about the mismatch between gallium arsenide and silicon all the time when you try to grow things on top of one another? That's been an age-old problem that's always existed.
Yes. So Bill's referring to the fact that if you try and grow these materials on top of the silicon, there's a lattice mismatch, it's full of defects, and they're very inefficient devices. And that's been the problem historically. So what we do is we grow them epitaxially on another substrate, and we bond them and then remove and reuse the substrate. So that bonding and reuse technology is the way people make SOI wafers today. So the whole silicon industry, particularly the memory industry, is based on bonding wafers together and removing and reusing the substrates. That's the technology we're using here. The advantage of that is because we bond it an epitaxially grown layer, the only dislocations are at the interface and they're edge dislocations. So we get away from that problem. Herb Kromer's in the audience. He worked for many years on trying to grow things epitaxially, and he often reminds me of how hard that is to do. So,
other questions? Okay. All right. So thank you. Thanks very much, John. So for our changing fields, our next speaker will be Dan Morse, who conducts research at the intersection of biotechnology and nanotechnology. Dan was the founding director of the Institute for Collaborative Biotechnologies, funded by the Army Research Organization here, and it's had a transformative effect on the UC Santa Barbara campus, working in the area of bio-inspired technology in the broadest sense. His research groups bring together disciplines of molecular biology, biotechnology, materials, chemistry, physics, chemical engineering, and this Renaissance man also started the Marine Biotechnology Center here. So, but today, within the Center for Energy Efficient Materials, he's been working on bio-inspired solar products and high-powered batteries, and he's going to talk about biologically inspired high-power batteries. Dan.
Thank you very much, Mike, and thank you all. It's a privilege and an honor to be with you. And to share some of the excitement of our group and our recent work on biologically inspired high-power batteries. This work is conducted through the auspices of the Institute for Energy Efficiency and the DOE-sponsored Center for Energy Efficient Materials that you've heard about. We heard a lot this morning about the vision for our energy future, and we're working to try to help enable that vision, the vision that encompasses alternative renewable sources of energy, electric cars, trains, ships, air and space launches, faster, denser digital information processing, and smart grid distribution systems. All of these, all of them they depend upon higher capacity, more powerful, safe batteries for storage of electrical energy. And we've heard several references to that dependency already today. The carriers of electrons and the repositories for electrons in storage devices are typically metals or metal oxides, semiconductors, and we drew our inspiration for the nanofabrication, the synthesis of nanostructured metals and semiconductors from biological sources. We need nanostructures in these metals and metal oxides because the small size will minimize the time of diffusion of the electrons in and out of this storage medium, the nanostructured metals. And our biological inspiration comes from the fact that living organisms, as illustrated here, make incredible structures out of silica. Silica is a semiconductor, and what's shown here are the outer shells made of silica or glass by diatoms, different species of diatoms. These are unicellular algae that are abundant in the world's oceans and fresh waters. There are nearly 1 million different species, suspected several 100,000 for sure. And each species produces its own remarkable nanostructured shell of glass. Every member of the same species produces the same structure. That inheritance tells us that the information for these structures is encoded in the DNA. And thus, we were particularly interested in the proteins that mediate these syntheses because we knew that, of course, that the DNA is the linear script for the structure, the synthesis and structure of specific proteins. We turned for a more tractable experimental system to certain marine sponges, which make their skeletons and defensive structures out of nanostructured silica. These are electron micrographs showing defensive structures, the bristly glass, multifaceted needles, and in this case, a remarkable hinged, mutually conformal hinged articulation of multiple structural elements in a sponge skeleton. This is a photograph of the skeleton of a deep-sea sponge that's nearly 1 foot in length, and if you look at it in close-up, it looks as if it's made out of woven glass. As we investigated this further, we discovered it's not woven at all, but instead the individual cells that produce these glass elements produce small needles that they position in three-dimensional space and then to form first the basket of this double overlapping quadrate lattice, which is remarkably strong and lightweight, and then they cement the elements together with silica or glass cement. There's a very interesting story about the efficiency of the structural construction here, which extends to practical lessons for architecture, but we don't have time to discuss that. Instead, let me say that we're also interested in the fundamental way in which this living organism can make structures of glass. Normally, in geological synthesis and volcanic formation of obsidian, or in human production of glass, it's necessary to heat the material to over 1,000 degrees and use very caustic chemicals. Here, living cells are doing this at low temperature, actually for deep water sponges, close to 0 degrees, close to freezing, and with no caustic chemicals. We discovered that the secret is that inside each needle of glass, there's an occluded protein filament that runs the full length of the glass, and it actually is an enzyme. It's a catalyst that catalyzes this low temperature assembly of glass, and at the same time serves as a template to guide the emergent structure of the needles. We used approaches of biotechnology and biochemistry to determine the structure of by gene cloning and genetic engineering, to determine the structure of this enzyme, this protein, and identify the parts of the protein that serve as the catalytic active site, providing the mechanism of catalysis for the hydrolysis and polycondensation of precursors that it will produce as glass. And we analyzed the structure of the protein filament with its multiple subunits here, the catalytic sites shown in green, extending actually several millimeters in length. And the way in which this protein with specific functional groups on the surface serves as a template to guide the assembly of the nanocrystals of not only silica, but also various semiconductors that we found could also be made catalytically. To gain a better understanding of this mechanism, we made biomimetic mimics of the catalytic site here, showing that if we incorporate the same functional groups, chemical groups that we identified by genetic engineering as essential for the catalytic formation of the silica on gold nanoparticles, we found that it is indeed the collaboration between these chemical groups that is all that's required for the catalysis. But wanting to take this to a practical level of translation, we asked, what are the lessons that are most fundamental, not unique to, let's say, not dependent upon protein structures or any biochemistry, but what is the underlying unique advantage provided in this biological system? And we realized that there are two. First, this enzyme actually works very slowly in the catalysis of synthesis of the silica from molecular precursors, providing an unusual kinetic control of the synthesis, bleeding in essentially the reactants as they begin to assemble, so that the weak cooperative interactions with the template, the protein surface, can control the emergent structures of the nanocrystals, providing a kind of vectorial control of crystal growth, regulating the polymorph, that's the kind of crystal, its atomic orientation and connectivity. Well, could we duplicate this without using biochemistry? We developed a method in which we provide the slow catalysis by diffusing through the vapor phase a catalyst of hydrolysis. It can be ammonia, vapor, acid vapor, even water vapor for some precursors. And as it diffuses through the meniscus of a solution that requires hydrolysis prior to the polycondensation to make the glass network, this diffusion through the meniscus provides a gradient, developing gradient of concentration of the catalyst, developing in space and time, that can accomplish much of what the biological does. And so translating from this molecular biological mechanism that we discovered, we developed a generic method, which is a low temperature, low cost, aqueous method for the synthesis of nanostructured semiconductor thin films and nanoparticles, either in a highly textured nanostructured thin film or nanoparticles. This is actually around the barium titanate. And this method turns out to be generic. We've made more than 50 different semiconductors using this method with unique nanostructures, and as a result of the novel structures, some uniquely useful properties. Furthermore, we've been able to convert the metal oxide semiconductors that are typically made by this process post-synthetically to either the metals, retaining their nanostructure, or metal sulfides, metal nitrides. And as a result, we have access to a number of potentially useful applications, including lightweight, high-power, safe lithium-ion batteries, low-cost solar energy, infrared detectors, and high-resolution 3D medical ultrasound. We're working with industry partners to explore the development of each of these, but the most exciting and most advanced of our work is in the area of the batteries, which I'll discuss with you. The typical commercial lithium-ion battery has as its anode graphite. It's relatively inexpensive, low performance, but fairly abundant. Decades ago, Sony scientists realized that they could get more oomph, more electricity, more capacity, more electrical storage if they somehow combined the graphite with metal nanoparticles, and tin is one of the best of these. Now, the problem is that why not just use, I should say, the tin has a higher capacity for lithium ions that will ultimately accept the electrons than graphite alone. Why not use metal alone? The problem with the metal is that when lithium ions diffuse into the metal, to form a kind of alloy, the metal expands fourfold in volume. And when the battery is charged and the lithium ion leaves the metal shrinks. And with repeated cycling, expanding and shrinking the metals are brittle. They pulverize. And they lose electrical connectivity. That's why our laptop batteries have to be replaced, because eventually they go dead. So smaller nanoparticles of metal, perhaps mixed with the graphite, Sony realized, might be advantageous. But the problem that they've encountered was that they tried to force that marriage by grinding the two materials together. If you look by eye, it looks as if you've made a mixture, but in fact, no intimate contact is actually achieved, and the performance is only marginally better. What we've done is we've taken that method that I described to you, biologically inspired, low temperature vapor diffusion of a catalyst into a solution containing little microparticles of graphite and an inexpensive solution of tin chloride. The catalyst hydrolyzes the tin chloride everywhere that it exists, including inside the interstices of the graphite, thus forming tin oxide in situ, growing the material as nanocrystals inside the graphite. Then, because the graphite is carbon, if we heat the material, this composite gently, it catalyzes a second chemical process, reduction of the tin oxide to metallic tin. The result is perfectly nanocrystalline tin nanoparticles grown in situ inside the compliant and conductive matrix of the graphite. Because the graphite is resilient, it can accommodate that reversible swelling and shrinking of the tin, the metal, as it becomes alloyed with lithium and expands, and as the lithium leaves. And so the result is an unusually high electrochemical capacity. The resilient graphite breathes to accommodate this large volume change, and so we have both very high energy density and high power density of this nanocomposite anode for lithium-ion batteries. This result shows, in the red, the progressive retention of electrochemical capacity, that's juice, as a function of ever-increasing speed of discharge. And I'll show you the value of that in a second. But here, notice that there's almost 50% retention at the exceptionally high discharge rate of 50 C. That's all the juice discharged in about a second. And here, full recovery complete recovery, very unusual, when we come back to the low discharge rate. So it hasn't been harmed by this process at all. Similarly, with multiple cycles of charge and discharge, we show only the first 20 or so, but this is now extended out to many hundreds. The nanocomposite doesn't fade when discharged at a moderate rate, whereas typical graphite progressively loses capacity. So it's high energy density, high power density. The value of this high power is shown here. Our cell phones, computers, and iPods operate in the range of about 0.5 to 1 C. Relatively slow discharges are all that they can support. Power tools can take significantly higher rates of discharge, from maybe 2 to 7 C. Electric cars in the range of 5 to 15 C. Trucks and military applications, well, beginning to go to 50 C. That's really the limit of practicality to use a battery. And so this material is exceptionally high power. Recently, we discovered that we can replace the graphite with carbon nanotubes. As many of you know, carbon nanotubes were a relatively recently discovered new form of matter. They're highly conductive. They're cost competitive now with graphite. Amazing. Industrially, multi-wall carbon nanotubes are now produced in kiloton quantities. And this frees us from the monopoly on a strategic natural resource, which is produced largely, actually the high quality graphite comes almost exclusively from China, which is progressively restricting its export of energy useful forms of carbon. But it's been very difficult to mix carbon nanotubes with metals or metal oxides to form good anodes or cathodes. We're extending our catalytic solution, just as I had described before. We suspend and disperse the carbon nanotubes uniformly in a solution of a precursor that we will then catalytically convert to the desired either high power nanocomposite anode or cathode. So it's just an extension of what I had shown you before. The carbon nanotubes, as made inexpensively, are agglomerates that look like chimney clinker. And they don't dissolve in any solution. But we found ways of dispersing them. And using these dispersed particles now of highly agglomerated carbon nanotubes, you can see the forest of these agglomerated nanotubes here. We again use our catalytic synthesis method to grow tin nanoparticles in situ inside the interstices of this compliant and conductive matrix. And the result here is an even higher energy density nanocomposite. Compare the performance to the carbon nanotubes alone. Interestingly, in this high resolution electron micrograph, you can see the evidence of what we are discovering seems to be an atomic level tethering between the bonding between the carbon nanotubes and the nanocrystalline tin. Perhaps, we suspect, explaining to some extent the high power of this material. This is an X-ray diffraction analysis of the nanocomposite, just confirming that all of the tin oxide that we've produced in the first step is subsequently produced to nanocrystalline tin. Highly pure. If we calculate the expected performance of these high-performance anodes in a combination with the conventional lithium iron phosphate cathode, we see that these anodes offer 10 times more power than present conventional and commercial lithium-ion batteries, and about a 40% higher energy density. Most recently, we have found we can extend this method generically to make high-power cathodes as well. And that, we think, is a breakthrough that will make this commercially viable. I show you here the result of our catalytic synthesis of a unique nanocomposite of highly crystalline, you see the facets, nanocrystalline, metal oxide, and the carbon nanotubes to make a nanocomposite. Because we're growing the crystalline metal oxide in situ in the matrix of these carbon nanotubes. The marriage between these materials is truly intimate. Here you can see that the nanocrystal has formed around the carbon nanotubes in some cases. And this high-resolution transmission electron micrograph confirms the uniformly high crystallinity of this material, confirming our X-ray diffraction results. Here's the electrochemical capacity of that high-power cathode, and it too is exceptional. It shows 98% retention of the original capacity after discharge at 10C. 80%, greater than 80% capacity retained after the exceptionally high rate of discharge at 20C. It's fully exhausted at 50C, but bounces right back. Complete recovery. And this curve here, these show that this is a very high voltage cathode at about 4 volts. Most recently, we've made a chemical substitution in this crystalline material, this crystalline nanocomposite, bringing the voltage up to closer to 4.3 volts. That's considered very high voltage, and with now 50% retention at the 50C, exceptionally high discharge rate. We've got the anodes, the cathodes. What about safety? I think Bill mentioned that this has been an issue for lithium-ion batteries. You know, we're able to use this method to make amongst the world's smallest and most uniform and highest purity barium titanate and barium strontium titanate nanocrystals with exceptional crystallinity. And as a result, if we sinter, that is, cook that material, it sinters together to form a ceramic. It's like firing clay suspension to make porcelain. And here you see the retention of the very small uniform nanocrystalline grains. So we're able to make from this, by sintering, the very fine grain barium strontium titanate, which retains this high crystallinity. And when we dope it with rare earth like lanthanum, then the material becomes highly conductive. Now, the reason this is useful is we're exploring the development of this material as a thin ceramic film to be coated on the electrode or current collector of lithium-ion batteries to make them explosion-proof and fireproof. It's essentially providing a fuse. Because of the way in which we've annealed and doped this material, we find that it starts out with very low resistivity. In other words, it's a semiconductor. It's conducting electricity. When heated above a certain temperature, the Curie temperature, here 130 degrees centigrade, the resistivity increases 10,000-fold. It switches from being a conductor to an insulator. It becomes like a fuse. And why that's potentially useful, we're all familiar with these news reports of the recall of millions of batteries by most of the lithium-ion battery manufacturers of the world because of the fire and explosion threat. The electrode in the lithium-ion battery is essentially like gasoline. Now, what we have found is that we can make a suspension of this ceramic and use electrophoretic deposition and anneal again to make very, very smooth, thin films of the requisite thinness so that, on the electrode, so that thin enough it doesn't block significantly block the ingress and egress of lithium ions or electrons, but thick enough to have enough grains to provide enough grain boundaries for this positive thermal coefficient of resistivity, this switch effect, to occur. And so we're getting here a 100,000-fold increase in resistivity, and we're exploring the incorporation of these first into small batteries to test their effectiveness. We've already shown that they protect a battery against a short circuit imposed from the outside. Now finally, I'd like to conclude by saying that the syntheses of the anode, the cathode materials, and this safety protectant that I've shown you, they're all chemical. It's not it's not the semiconductor fabrication method that's used to make high-performance computer chips or the photonic materials, which of course warrant the high price, but batteries are close to commodity material. We've got to drive that price down. And so what we've shown is that from the laboratory scale, where we were first making 100 milligrams by diffusing the catalyst through into a dish containing a small solution of the precursor, we've now scaled this to produce a couple of 100 grams with retention of full crystallinity and the same original crystal nanocrystal size and purity as in the lab scale. And now spinning this out to a small company that we've started here in Goleta, LifeCell Technology. We are now getting to 2 kilogram batch production that's in batch mode, and we've recently found that we can accelerate the throughput of this synthesis process by combining the vapor stream of the catalyst with micro droplets of the precursor solution so that the reaction occurs between vapor and micro droplets for much faster diffusion and much higher continuous throughput. So to try to enable the vision that we all share here, I've shown you the work that we've developed in using our biologically inspired, kinetically controlled low-temperature catalytic nanofabrication, which offers batteries with exceptionally high power, even at the exceptionally high discharge rate of 50 C, with higher cyclability and stability, increased safety, readily scalable. Scalable means affordably scalable manufacturing. And I've shown you that this is a generic platform technology with a broad range of applications, and we believe that this is now opening opportunities for strategic industry partnerships. And we very gratefully acknowledge the support we've received from the Center for Energy Efficient Materials, the Institute for Energy Efficiency, and Department of Energy. Thank you.
So, Dan, thank you. And I bet you haven't heard a battery talk that started out with sponges and diatoms before. So, any questions for Dan? Yes.
The material with the positive coefficient is that fused burn, or is it recyclable many times?
It's recyclable. We've only done it about a half dozen times. But you don't actually, well, I think at that point you want your battery management system to pull that cell out of the system, out of the pack, isolate it. That saved you from the explosion, right? That saved you from in a battery pack. And right now, as you know, vehicles like Teslas have thousands of 18650s. They're about the size of my thumb, right? You don't want one battery igniting, exploding, and setting off a chain reaction with others, right? Because of the intense heat. And so you stop the short from igniting that battery, pull it out of the circuit with battery management. Does that make sense? Yeah. So you don't want to keep cycling.
And then
You don't want to push that.
the other thing is your thin film, you lower the temperature down to 50 degrees C. Is that something you wanted to do?
Oh, no. We now see that linearly, inversely proportional to the content of strontium, we can tune that fuse point, that Curie temperature, the temperature at which it converts from any place between 50 and 150 centigrade. And we can tune that precisely and reproducibly.
Okay, so we had one other question here.
In the last process that you
There's a mic.
described,
Yeah.
in the last process that you described, making the 2 kilograms, how long did that take to make two kilograms?
The synthesis time is a few hours.
Only a few hours.
Yeah, well, that's the first synthesis of the nanocomposite. It then requires annealing, right?
But still, to form your base substance, it only takes, that's
Yeah.
remarkable.
Yeah.
Thank you.
The reactor took a lot of engineering. There is a lot of viscosity, viscometric feedback control. So as the reaction is going, we sense the progress of the reaction and control the rate accordingly. So we pushed it as far as we can while still getting the high performance.
Thank you.
Okay, all right. Thank you very much. Thanks. Okay, so in our tour through the Institute for Energy Efficiency, our next speaker is Jim Speck, who's professor in the Materials Department, which, as you've heard a lot about today, and he was one of the inaugural class of fellows of the Materials Research Society. He's one of our stellar members of the Nitrides group here, director of the Interdisciplinary Center for Wide Bandgap Semiconductors. And his talk will be the end of the light bulb as we know it, the dawn of solid-state lighting. So a challenging topic.
Okay, thanks very much. Which is forward. Okay, great. So thanks very much. It's a great pleasure to be here today, and I think I'm one of the few repeat speakers from last year, and so I'll start out with a question from last year. And this is work, at the end of the talk, I will highlight just a few of the highlights going on that's actually funded by the Center for Energy Efficient Materials under the nice, great support from DOE. Much of the work that goes on in lighting at UCSB is in a center that's entirely industrially supported called the Solid State Lighting and Energy Center. That's led by Steve Denbars and Suji Nakamura. And with Umesh Mishra, Steve, Suji, and I have worked together in a barrier-free collaboration for about 18 years, and Suji came on board over 11 years ago. So that's really the core of our activity in nitrides. So in the outline, I'm just going to give you a brief primer on light and lighting. This comes back to a question from last year, and then talk about the impact of solid-state lighting on the energy equation, a little bit about the technology and economics of solid-state lighting, and then just a little bit of highlights of UCSB efforts in solid-state lighting. And the goal of this, of course, is right now in the lighting age is that we're somewhere between incandescent lights and various forms of compact fluorescent lighting. The goal in our lighting center is to end the last tube technology. This is just a housing on an early manifestation of an Edison socket replacement light bulb, but there's no tube in this. And so this is the last tube technology, and the goal in our center is actually to kill this tube. The big issue in killing the tube, this last tube technology, is actually economic now because all the other pieces are largely in place. And so first, this was a question last year, and this sort of troubled me because it's a little bit of a complicated definition. So what is light and how do we define it? And so I know this is a little bit confusing. This goes back to archaic units that are tied to a candle. A candle is a very poor form of illumination. How do you make a candle? You take a piece of string, right? It's soaked and waxed, and then the wax will wet up that stream. It will vaporize the carbon, and then you actually have luminescence from carbon black. That's a candle. A candle gives off very little light, right? And then the units of a candle go back to something on the order of furlongs. It's something like the light intensity that your eye would see at 1 foot from a standard candle. So this is an archaic unit. It's amazing that it survived as becoming an SI unit. It's amazing. And so we had a question last year, what's a lumen? So I have to explain what a candle is first, and then we'll go to a lumen. And so the candela is a unit. It's a luminous intensity approximately from 1 candle, okay? This includes what's called the radiant intensity. This is properly in SI units. This would be in watts per solid angle, okay? And then the luminous intensity includes the human eye response. And as I'll show you in a moment, the human eye sees the best at pure green, okay? And as we go to longer wavelengths towards red or IR, we see less and less efficiently. And the same if we go to higher energies, shorter wavelengths, towards the violet, we see less and less light. And by the time light has a wavelength much less than 400 nanometers, we can barely see anything at all, okay? So the luminous intensity includes a function that goes back to these archaic issues of the candle times the human eye response, which is normalized to 1 at true green light, times the radiant intensity, which is in proper SI units. And then the lumen, which is what we call luminous flux, and this is usually what you buy when you buy lighting, okay, is just the luminous intensity times solid angle. So a candle, a simple table candle, for example, gives off 4 pi steradians, and so that's a solid angle of a sphere, okay, times approximately one candela, so about 12 lumens. And a 100-watt light bulb, and this is the important number that everybody can sort of wrap their minds around, a 100-watt light bulb gives off approximately 1,000 lumens, okay? And if you go to Home Depot today you can easily buy a 100-watt light bulb if you buy it in a pack for something well south of $1, right? And so that's an important number, because in your mind, you want a lighting product that's about a kilolumen for something south of $1. Okay. Now, if you're eco-conscious and also can do the arithmetic on lifetime, you may fall to the temptation to buy something much better in efficiency, which is a compact fluorescent light, okay, for a subsidized price somewhere between $2 and $5, right? And that's giving out something on the order of it. And then if you go to Home Depot today, you will actually see a section on the shelf of solid-state lighting products, and it looks great until you look at the price tag and you see something on the order of $50. And it's not 1,000 lumens, it's probably half of that. That's the big challenge. There are many other technical challenges, but those are the real challenges. Okay? So we talked about this. This is the human eye response. This is called the eye response function as a function of wavelength. Everything that we do in lighting is between violet and red. What Professor Bowers talked about in his very nice talk on optical communications is typically done at about twice this wavelength, either at 1330 nanometers or 1550 nanometers, okay, out in the IR. Where we make LEDs primarily is with blue LEDs with a gallium nitride material system. We can also make pretty good but not great green LEDs. And as we go to longer wavelengths in the nitride systems, we struggle, but coming from the conventional 3,5 materials, arsenides and phosphides that we heard a little bit about earlier this morning, can make extremely good LEDs, but not so good orange or yellow LEDs. And so I'll talk about this a little bit, okay? So making really good devices in the green is a real dream of us long term, because this is by far where there's the highest efficiency. And this is what's called the luminous efficacy, fundamentally, that if we had a perfectly efficient light source in lumens per watt, that in the green, it's on the order of 680 lumens per watt, and quickly falls off in efficacy as we go in either direction. This is because of the human eye response. Okay? And then a little bit more on light. Okay, this is what's referred to the CIE diagram. And this is a little bit of a complicated concept, but this is how to take something linear, which is just wavelength, and wrap it around to capture how the human eye perceives light. Okay? And so if we take light here, for example, which is violet blue, and if we were to combine it with yellow light here, and with the right color mixing, to the human eye, combining two different colors would appear to be white. And this is the basic game that we play in solid-state lighting. And if we look at the possible efficiencies here, and I'll compare these in a moment to the efficiencies of existing light sources, okay? These are the fundamental theoretical efficiencies, and anything on this locus here, so you see these are all contour lines of efficiencies, okay, for different light sources, okay? The highest possible efficiency is in the green, which is on the order of 680 lumens per watt. If we go along this locus, which is referred to the Planckin locus, this is what white light would appear to be. And this white light along this locus appears to be colder and colder as the color temperature goes up. I know that's counterintuitive, but higher and higher color, higher and higher temperature flames that go from being a dull orange to a bright red to a blue to an incredibly bright white. That's the black body radiation from the luminescing particles, okay? And so ideally, the ideal light source would have a color temperature about 2,700 degrees Kelvin. That's the color temperature of an incandescent light bulb, and that's what you're familiar with, okay? That's what we call warm white light, okay? If we have higher color temperatures where the efficiencies are around here, which would be around 5,000 degrees Kelvin, okay, that's what we call cold light, okay, and that's what you would see in a typical poor quality fluorescent light bulb. It looks sort of bluish, it has a cold feel to it, okay? And so this is a space that we work in solid-state lighting. The typical way that we do this is that we take a blue LED and we combine it with phosphors such that we land on the Planckian locus so that we have high-quality light that looks like black body radiation from light, okay? And these are just comparison of conventional light sources. Really, no perfect artificial light source exists yet. In terms of color quality, probably by far the highest quality, color quality light sources are incandescent light sources. The advantages of incandescent light bulbs is it's a great product. It's very cheap. It has great color quality. Lifetimes are typically very short, a few thousand hours. And as we'll show in a moment, very poor efficiency. Fluorescent light bulbs are sort of the next candidate for general illumination in terms of light, okay? Typically, fluorescent light bulbs have cold color temperature, okay, intermediate efficiency, intermediate lifetime, and is a concern of ours in the long term is that even a simple CFL has something on the order of 5 milligrams of mercury in it, okay? And so this is also a life safety issue. Halogen lights are a fantastic point source of light, very short lifetime, very poor efficiency. And then for outdoor lighting, high-intensity discharge lights are quite popular. Major issues with high-intensity discharges is that they typically have very, very poor color quality, actually very difficult restart and start issues, and very short lifetimes. So somebody asked me, what's the sequence of lighting that solid-state lighting will knock off, okay, in terms of markets? For illumination, the first thing is it probably will happen will be halogen, okay, because of the specific properties of LEDs. And then I think it will be a tie between knocking off either incandescent or different manifestations of fluorescent, okay? And then for outdoor lighting, this is already starting to happen in terms of knocking off high-intensity discharge, okay, because of the light quality and because of the very, very long lifetime of LED-based lights. If you go again to Home Depot today, you will be able to find very expensive, very early generation solid-state lighting replacements, okay? These are just examples maybe of a year back of Philips light bulbs, okay? The efficiency of these is okay, okay? It's not great. The total light output of these, if you see here, these early generation solid-state light bulbs, these are on the order of 200 to 300 lumens. They're about 1/3 where they need to be. They have real issues with the overall design. So in terms of the engineering and the efficiency and the cost, this is the space that the whole industry is working on so that we have something in these two examples of a Edison socket replacement. Conventional light bulb has to improve dramatically in terms of engineering. We have a little bit more space replacing directional halogen lighting, okay? So coming to efficiency, this is fresh off of the press. This is from the DOE solid-state lighting multi-year plan. If you type into Google DOE and solid-state lighting, it will directly take you to links. This multi-year plan is a beautiful report from DOE. This is the newest generation that was just published. Oh, it says March. It just came online live about a week ago. And so this shows the luminous efficacy in lumens per watt as a function of time. And if we start with these archaic technology, incandescent light bulbs have basically been flat ever since Edison at something between 10 and 20 lumens per watt. And halogen light bulbs, slight improvements on these, but typically halogen light bulbs have luminous efficacies of about 20 lumens per watt. If we, please save me. Thank you. Okay. And if we start comparing to the real competition, we don't see this as competition. We just see this as cost. Fluorescent light bulbs, CFLs are typically at efficiency of about 60 lumens per watt with not any reason to improve dramatically. Linear fluorescents typically have efficiencies on the order of 80 lumens per watt. If we look at the evolution in solid-state lighting, this is real product efficiencies, but lab demonstrations in solid-state lighting, the record lab demonstration for white light now is Nichia, actually at 250 lumens per watt in a laboratory demonstration, okay? And at theoretical limits, well north of 300 lumens per watt, we're optimistic that in time, with good engineering and science, we can get there, okay? We think ultimately at 2020 timeframe that we should have fielded technologies easily of 150 lumens per watt, but really possibly well north of 200 lumens per watt. That's where the field's heading. This is data that Danny Fiesel, who's a senior researcher in our Solid-State Lighting and Energy Center, put together. This is a very interesting number. He spent quite a bit of time looking at electricity consumption in California, getting data from online. And what's very interesting in this data, this is the most aggressive number that I've actually seen on lighting consumption of electricity. In California, interior lighting uses 28.7% of electricity, and exterior lighting is about 6%. So electricity consumption due to lighting is on the order of 35% in California. This probably does not take into account the fact that lighting is actually a fairly good heat source, and that means that when we're in warmer times of the year, you're actually air conditioning to overcome the lighting. So there's actually additional air conditioning load due to lighting, okay? Which is actually a real issue in buildings, okay? And so you see more conservative numbers on the energy impacts of solid-state lighting. This is from information from the DOE solid-state lighting website. This is fresh data I just pulled off the web a couple days ago. But if you look at 2030, anticipated energy savings from solid-state lighting with reasonable estimates of market penetration in 2030, I think these are conservative numbers. At 150 lumens per watt, what you will find is that DOE estimates 190 terawatt hours of energy savings. So that's the equivalent of 24 full gigawatt power plants. Almost all power plants are on the order of a gigawatt, or about 31 tons of CO2. These conservative estimates are based on 20 to 25% energy consumption. So just to change gears a little bit, how do we make light from LEDs? So the basic idea in LEDs, unlike the silicon that John was talking about, but the compound semiconductors that he was referring to, is that we have carriers which are positively charged called holes, and we inject these and have them meet electrons. So this is the absence of an electron, a hole with electrons. In a direct band gap semiconductor, if we do things properly, we can have a very high success rate of making light. And then if we really work hard, we can coax that light out of the high refractive index semiconductor. So the material systems that we work on are all direct band gap semiconductors spanning band gaps from the deep ultraviolet in the aluminum nitride material system to the near ultraviolet material system, gallium nitride, into the fairly far into the infrared with indium nitride. And by alloying indium nitride with gallium nitride, we can span the band gap range in the visible, particularly from violet to blue towards green. And then the real structure of a light-emitting diode looks like this. This is research supported under the SEAM Center at UCSB. This is an atom probe tomograph. This is about 100 million atom data set, actually looking at the atomic structure. So every little pixel in here would be a single atom that we record sequentially. In producing this, this is the P side of the semiconductor where we inject the holes. This is the N side of the semiconductor. And if we do this well in the material with the right energy band gap, so this produces the right radiation of light, and these are the indium gallium nitride quantum wells, this is where we actually produce the light that then we have to coax out of the semiconductor for the solid-state lighting. Two main approaches for solid-state lighting is to take different color LEDs and mix these to make white light. This has not gotten very much traction in the field for two reasons. One, the green emitters are not sufficiently efficient now. The blue emitters are very efficient. And actually, the drive electronics for this still looks difficult, okay, to get good color mixing and combined with binning issues. Whereas the primary approach for making white light is to take a blue LED and combine it with a yellow phosphor or a yellow phosphor plus some other combinations of phosphors. And to the human eye, blue plus yellow looks white, okay? And this is the way that we do it, okay? And then the impact that this has already had in lighting, if we just look at market sizes for lighting, okay? And it's very interesting how technologies, unexpected technologies drive lighting. What really got gallium nitride-based LEDs off the ground for technology was actually initially having keypad lights for cell phones. And then the screen on cell phones is actually illuminated with white gallium nitride LEDs. And until recently, this was the largest market for LEDs. And then you've seen this transformation. Almost all computer monitors, laptop monitors, have gone from what are called cold compact fluorescent light bulbs to LEDs along the side of it. And now TV sets, okay, which are illuminated with what are called backlighting units. They're really side lighting units. And we call this the backlight unit market, BLU market, is actually driving this. Right now, the total market for high brightness LEDs is on the order of $20 billion. What we anticipate is about 2015, it's going to be the tipping point where the LED market is going to be driven by lighting. And it's about 2015 that in the marketplace, a year earlier or a year later, that one should actually be able to see reasonably priced LED-based lights. So that's the tipping point. And then the total available market for solid-state lighting in 2020, we anticipate to be something on the order of $50 to $100 billion a year. I have seen market studies out of Wall Street where this number can be as high as $120 to $150 billion a year. So this would be by far the second largest semiconductor application. So I just want to talk about two other things very quickly. So in solid-state economics, this is our sunshot, and we also have a sunshot. We haven't described it, but the solid-state lighting targets for 2020 are actually out of DOE, and this is in the DOE multi-year plan. So I pulled this out of the DOE multi-year plan that just published, is to get to what's called an LED package price. So this is the light engine of, by 2020, to get to $1 per kilolumen. What you actually see in industry and industry targets is to have the whole light engine at 50 cents that's producing 1,000 lumens, and then the whole electronics plus base plus luminaire plus package at 50 cents, so that combined it's $1, so that at the retail level it would be on the order of $3 to $5. And so that's our sunshot. Okay, what's happening in the industry? What we're really finding in the industry is that as the industry is growing, of course, more people see that it's interesting and want to get involved. But the other thing that we see is that more and more people are entering the industry from the silicon side. And then when people enter from the silicon side, they actually understand how to scale cost, manufacturing, and that's driving it very hard now as it's starting to run. So, can I have 1 more minute? 2 more minutes? Okay. Okay. So let me just give you a couple examples of what we're doing at UCSB. If somebody said, what's the biggest issue today in solid-state lighting on the science and technology side, it's what's called efficiency droop. And what efficiency droop is a phenomena that if we look at the slope of the light output with drive current, it tends to roll over. So as we put more and more current into the LED, we're getting more light out, but less and less at a slower and slower rate. And so if we look at the efficiency as a function of drive current, we'll hit a peak efficiency at a very low drive current, and the LED will actually run less and less efficiently. And this gets worse and worse as we go to longer wavelengths. The leading theory of this is a process called indirect Auger. Chris van der Waal, under SEAM support at UCSB, has just published a very important paper in APL. This just came out last week, where he's done fundamental density functional theory calculations of this 3-body process. So these are actually very challenging calculations, and actually predicted fundamentally that a phonon-assisted, or what's called indirect Auger, is the cause of droop. Claude Weisbuch and I have experiments underway to see if we can get a direct experimental signature if indeed this indirect Auger process is a cause of droop. Droop is a major issue because as we drive the diodes harder and harder, they become less efficient. So the solution to have them efficient is to use a lot of area, and then the cost goes up. If we can solve droop through design of our epi-active region and new orientations, then we can get a real economic gain. This is a massive issue in solid-state lighting. Another issue that was pioneered at UCSB is new orientations of gallium nitride that we call nonpolar and semipolar. And we've already shown with our data at UCSB that we're able to fill this poor efficiency gap in the green region. And we're very optimistic with continued science and engineering that we can fill the green gap. And so this is another area we're looking at. In an area that's already in modern technology, if you go out and buy the high brightness LEDs from Cree or Philips Lumiled or Osram, what you would, and if you ripped it apart and looked at the emitting surface, you would find microcones. This microcone technology was developed by Suji Nakamura and Evelyn Hu in the early 2000s at UCSB. And thanks to the great support from Cheryl Mills-Englander and her team at TIA, this is patented now, and this is the dominant technology for light extraction in high brightness LEDs. That's a UCSB invention. Claude Weisbuch and I and others are working very hard on photonic crystals, and our own data on photonic crystals is showing that we can get better light extraction from gallium nitride-based photonic crystal LEDs over rough LEDs. That's all UCSB technology and IP. This is a new important paper from Liz Rangel, who was supported under SEAM, that just came out in APL showing this improved directional light extraction from high-performance photonic crystal LEDs. So those things are really happening now at UCSB. And I think the main thing that I want to say in prospects is that our technologies have actually been driven by unexpected markets. The market that is surprisingly really giving a big boost to solid-state lighting is backlight units for LCD TV. This is giving us a huge unexpected scaling in the industry. And again, because I know there are great talks this morning about the Sunshot Initiative in solar, the lighting side of it, we have a sunshot, and that's to get to $1 for a kilolumen. Okay? When that happens, all lighting technology will be solid-state lighting. Good, thanks.
Okay, so Thank you, Jim. And so we'll be making book on whether they get to a dollar per kilolumen before the dollar per watt. So that'll be that you can make your bets outside. Okay, so questions here. Questions for Jim? Yeah. Yeah, there's a microphone here.
I'm Ivanet from San Jose. Thank you for that presentation. I'm very concerned about the kind of color chromaticity. Maybe kind of LED is an independent power generation, but the sun beam is a continuous beam. So maybe the how to see our objective product in a lighting, under the lighting is a kind of issue. So there's some proposal of the color quality scale. Do you know?
Yeah, so there, one of the main color quality scales
Yes.
is how close an LED light
Yes.
matches an incandescent light. And this is called color rendering index.
Yes.
So the two main things that when we look at white light, we talk about the color temperature. Higher color temperature looks bluer, colder, okay? And color rendering index, which is how well the LED fills the full spectrum,
Yes.
okay? And an incandescent light bulb, by definition, has a CRI of 100. Good solid-state
Yes.
lighting LEDs have CRIs in excess of 90. Poor ones that you would see that would look bluish or yellowish might have CRIs well south of 80. Okay, so the issue of color quality is a huge issue in the industry. It ties to both what the primary LED color is,
Yes.
but also an enormous, and it's been a great renaissance for phosphor research, because there's an enormous amount of research now in phosphors that are pumped by LEDs that will emit, other than yellow, but good green phosphors, good red phosphors. There's a huge race on for good red phosphors. There's also a race on for alternative yellow phosphors, and even for blue phosphors.
And so do you foresee that it's kind of a color quality scale can be some standard, or?
I think there's still controversy on what the best color
Yes.
quality standard is. There are other indices like the Munsell index that look more evenly over many wavelengths. I think this will be fought out in standards. DOE's been fantastic in helping, through the solid-state lighting program, helping provide leadership in defining industry-wide standards. And even though the industry, unfortunately, is mainly centered in Asia, the Asian lighting industry looks to DOE for leadership in standardization. Absolutely, they do. Yeah.
Okay, maybe one more question? Okay.
Just one.
Yeah, sorry. Yeah, Bill. Bill, right in front of me.
Well, I'm curious, do you have ideas about what to do about this droop?
So, well, we have a bias. So droop goes as a cube of the injected carrier density, okay, just from polynomial fits. And there's controversy on the physical origins, whether it's Auger, or it's carriers overshooting, or there's another theory called delocalization, which enhances non-radiative rates. All of the solutions are generally solved by going to thicker quantum wells, so that we have more active volume, lower 3D carrier density. In the nonpolar, semipolar orientations that we developed at UCSB, we have a freedom to go to any quantum well thickness. So, yeah, we have a lot of ideas how to do it.
Okay, great. Thank you, and thank to all of our speakers today. Thank you. Okay, it's time for a break, and we'll gong you back in after the break.